Okay, I want you to get your homework out from Monday, 3-5 day 1, and I want to do a few questions together. Some of these, the trickiest part I think is the simplification, and that's why I say check your odd ones in the back so you can see how they simplify it. Sometimes it's a stretch, but sometimes it's not that much of a stretch. So let's look at a couple of those real quick, like number 7. Right, y equals 4 over cosine x. You do have to do the quotient rule there because if you try to bring cosine up, it becomes cosine to -1, and we don't know how to do that yet. Um, so quotient rule, if I take the derivative, then the derivative of 4 is 0 times the bottom minus, leave the top alone, and the derivative of cosine is negative sine all over cosine squared. So this just goes to 0. These negatives cancel out, so that just becomes positive 4 sine of x on the top over cosine squared x on the bottom. And if you look in the back of the book, that's not the answer. And so this is an example of one that I think, it would be a valid one to give you on a test or on a AP exam for multiple choice, because you should be able to look in the back of the book and see that there's a tangent and say, oh, sine over cosine is tangent. And to think about that, you could break that bottom up as cosine x times cosine x. And it's multiplication. You're allowed to break multiplication up. And so you can think about sine of x over cosine of x is tangent. And if you want to think about having a 1 left over here, 1 over cosine x is secant. So that's where the back of the book gets an answer of 4 tangent x secant x. And again, that's why I say check the back of the book, because otherwise you might not get there. Number 9 is kind of a crazy one in terms of simplifying in the back of the book. I will tell you, like, you have to multiply the top and the bottom by sine squared. Probably one that I would say not that super important that you check the back of match the back of the book. If you really want to see that tomorrow when I come back, I can work that one out for you, but I want to skip to some other ones that I find to be more important here. Let's see. I really do like 25 that I asked you to kind of prove those using the quotient rule. So, like, I'm not going to do 25 for you, but like on part A, where it says prove that the derivative of tangent equals secant squared, well, tangent you could write as sine over cosine. So if I asked you to take the derivative of sine over cosine, which is just tangent, prove why the derivative is secant squared. So do the quotient rule for number 25, and you should end up with secant squared. So it's kind of like a proof there. So if you didn't get that, you could go back and do it. I do want to look at 31, though. 31 is a 2-part question. They give you this lovely picture, and they ask you 2 things to do. It says, part A, find the tangent to the curve at P. So if you look at that picture, at point P, they give you the point pi halves 2, which is the same questions over at like 21 that they ask you to find the tangent. The difference is they just give you the graph here. They also give you the equation underneath. And so if I'm going to find the derivative of this, the derivative of 4 is just 0. The derivative of cotangent is negative cosecant squared x. And the derivative of cosecant is negative cosecant cotangent. So I'm going to go ahead and change that to a positive 2, because those negatives would cancel out. And maybe one of the tricky parts of this is you have to find the slope at pi halves. The nice thing is pi halves is not that bad to plug in here. So you get negative cosecant. I'm going to just say negative cosecant of pi halves squared, because that's how I'm going to think about evaluating that. Plus 2 times cosecant of pi halves times cotangent of pi halves. Well, think about pi halves. Pi halves is up here. That's the point 0, 1. So the cosecant of pi halves, cosecant is 1 over sine, so that's going to be 1. So negative 1, because 1 squared is 1, plus 2, and again, cosecant of pi halves is 1, and cotangent of pi halves, cotangent is what? X over y, so it'd be 0 over 1, which is 0. You got to be able to do these basic trig functions. So I think our slope here should be negative 1. So our slope is negative 1 at the point pi halves 2. So I can write my equation as y minus 2 equals negative 1 times x minus pi halves, which I think should be your answer for part A. Part B gets a little crazy here. I'd be interested to find out if you guys did this any differently on part B. But part B says, now find the horizontal tangent to the curve at Q. Notice Q is a different point than P because they want to know where does it have a horizontal tangent, which means where would the derivative equal 0. So for part B, I'm going to say I need to set that derivative equal to 0. And the derivative was negative cosecant squared x, or t, I guess it was, wasn't it? T, was it t or x? Why do I have two different things in here? It was x. Why do I have t on there? That's really weird. Okay, sorry. X plus 2 cosecant x cotangent x. And I want to set that equal to 0, which means that's making me go back and think a whole lot about trig equations, solving that. We could factor out a cosecant there maybe, and we'd be left, yeah, maybe that would be the way to go. Oh no, we'd still have cosecant and cotangent left. I have a bunch of eraser marks on my paper because I really did try that first. I tried to factor out a cosecant, and it would have been really great if what was left would only have cotangent in it, but it still had a cosecant and a cotangent. So it didn't work. I couldn't think of an identity to use. Maybe one of you did, and that worked out better, because cosecant squared and cotangent squared are somehow related. What I did is, like, the last resort when solving equations is I changed them to sines and cosines. So I changed this to negative 1 over sine squared x plus 2 over cosecant would move sine to the bottom, and cotangent would be cosine over sine. And so notice that this is like this becomes sine squared over here. So these are like a common denominator already. So I could say that this is negative 1 plus 2 cosine of x equals 0. If we, I don't know how you want to think about it. You could think about if you multiply sine squared over times 0, it cancels out. But could that be a solution? I said, what if I thought of it like this? If I took out the, like, what if I took out like a 1 over sine squared x, and I was left with the negative 1 plus 2 cosine x, kind of separating the top from the bottom there? And then I broke up that multiplication and set each one equal to 0 to solve it. This is an example of a problem that you could have just multiplied the denominator over and it would have canceled out, but sometimes it doesn't, so I didn't want to tell you to do that. But when would this equal 0? It's never going to equal 0 because we can't have something that's going to make 0 in the denominator and 1 on the top. So this really is not important to this problem. But on this side, I could add 1 over and I could divide by 2. And I get cosine of x equals 1/2. and it says, you know, where's that true? Where does cosine equal 1/2? And you might say, well, there's a lot of answers there, and I guess you could say that, but that's why they give you the graph. Notice the graph point Q is somewhere between 0 and 2 on the x-axis. So you know that it's in the first quadrant, and you know it's not like a multiple of 2 pi, like around the circle again, because you can look at the graph there. So where in the first quadrant does cosine have a value of 1/2? And I think that it is, cosine is the x value. So 1/2 square root of 3 over 2. I think it's up here at pi thirds, right? 1/2 square root of 3 over 2. So we could say that at x equals pi thirds, we know that's true. This is kind of a crazy problem because we're not even done yet. We want the horizontal tangent, which means we want to find the tangent there, which means you have to tell me, what do I get? Like, what's the y value when I plug in this x value? And that means we're going to have to go all the way back to the original equation to find the y value, right? Which was 4 plus cotangent x minus 2 cosecant x. And I'm just going to plug pi thirds in there. Oh my gosh, I'm so out of room here. I might, I don't even know what I'm going to do. Erase over here. Y equals 4 plus cotangent of pi thirds minus 2 cosecant of pi thirds. This is where you have to be able to do this without a calculator, using your unit circle or your triangles. Cotangent is x over y. So that would be 1/2 over the square root of 3 over 2. And cosecant is 1 over sine. So, or just flipping that over, 2 over the square root of 3. Is that right? Last year, I believe it was Philip that came up with the plan, which is always true when you simplify these, that since these denominators are the same when you flip it over, those are just going to cancel out. So you end up with 1 over the square root of 3 minus 2 times 2 is 4 over the square root of 3. So I don't know, it's kind of weird to have that in the bottom, but that would be 1 minus 4 is negative 3 over the square root of 3. Think about if we rationalize that denominator there, we could multiply this part right here just by the square root of 3 over the square root of 3. And we would get, what, 3 radical 3 over 3, or just the y value equals 4 minus the square root of 3. Now that's really just the y value, and you might have already looked in the back of the book and say, well, that's what it says is the answer. Well, that's because, think about what the slope of this is. If we're talking about a horizontal tangent, right, we're talking about a slope of 0. So if we take y minus the y values, which actually make that plus 4 radical 3, equals 0 times x minus pi thirds, this whole side goes to 0. And so the reason they got this in the back of the book is they just added that over, or added and subtracted that over. And that's where they got their answer, because the slope is 0. That's kind of a crazy question. One more I want to look at really quickly is 37. We've seen questions like this before, talking about continuous and differentiable with piecewise functions. You've got to be able to know what to do to set up these problems. It says, is there a value of b that will make this function continuous at x equals 0? Differentiable at x equals 0? Give reasons for your answer. Continuous at x equals 0 has nothing to do with the derivative, has nothing to do with the slope of the line at that point. It has to do with, do these meet up? Is there a gap? You could try to graph it, but you want to figure out what b is. So remember what that means. If it's continuous, it means they equal each other. So x plus b has to equal cosine of x at the point where they meet up, which in this case is x equals 0. So plug 0 in there for x and solve for b, which means you just get that b equals cosine of 0. So b equals 1 would be what makes it continuous, because if b equals 1, then the pieces meet up at x equals 0. Right? That's continuous. We did that all the way back when we first talked about continuous functions. You could say the limit from the left equals the limit from the right. That's another way we could say that something's continuous. But what about differentiable? If we want it to be differentiable at x equals 0, that means that the derivative from the left, I can't spell left, has to equal the derivative from the right. Because even if they meet up, right, even if it's continuous, it could still be a sharp point or a cusp, which would make it not differentiable. So let's just take the derivative of the top and the bottom. If I take the derivative of this, where b is a number, the derivative of x is just 1, the derivative of b is 0. If I take the derivative of the right side of that graph, if I take the derivative of cosine, I get negative sine of x. It could ask us where is the derivative equal to each other, but it doesn't. It tells us, is it differentiable at x equals 0, which means now plug in 0 to both sides and see if it equals each other. People get confused by this side because how do you plug 0 in there? But again, think about x plus b. X plus b is a linear line, so the slope is always going to be 1. So the slope of this side is going to be 1. But what about this? If I plug 0 in here, does 1 equal the slope on the other side of negative sine of 0? And I get that that's not true. So give a reason for your answer. Not differentiable at x equals 0 because the left, why can I not spell left? Left derivative does not equal the derivative coming from the right. All right, that's kind of an AP style question there. So if you don't have these all finished, you should do that today because test is coming up very soon. Also, I've helped other people with other questions, so maybe if you have a question I didn't go over today, someone could help you on that. That doesn't mean just copy their answer. That means help you, walk you through it, answer your questions. I've also left a worksheet for you, which is just over product quotient rule with a few trig things thrown in there. I will tell you the very last question is a little tricky. Do your best on it. I'm sure that's one that we'll talk about tomorrow, but try it. It's not that long of a worksheet, which means if you're behind on homework, then hopefully you can catch up on some of that tonight. Test next Monday because we lost a day yesterday, so we'll do 3-5 day 2 tomorrow and review on Friday.